AC signal. So then I have to modulate means I have to add these two, right? So to add, we can easily use that summation amplifier, right? Remember last time we talked about summation amplifier. One input is this one, other input is this one. Then your output will be this DC plus AC, right? So that way you can modulate the signal. Then you have this your DC signal modulated with your AC signal. So that's the one we are going to apply to your sample. So then the output, then you have to demodulate. To demodulate, we can use the lock-in amplifier. That's the whole idea. So then at the end you extract this signal. This is what we are interested in, right? Yeah. So not this any of these. But and after this one, we are taking this to the lock-in amplifier. So from there, you eventually get this, your real signal. So whatever buried in that noise, you can easily get back. So the modulation is, there are different ways of modulating that one. If you have an electrical signal, you can modulate with that some AC electrical signal. If you have an optical signal, so to modulate, there are different ways. I don't know whether you're familiar with something called the chopper. So chopper is you just take the only part of that signal, right? So if you have some chopper wheel here, you just cut out some, this is the chopper wheel, right? All these things are you get the idea, right? So you have this places. If you have light signal, when this is rotating only, when it is passing through here, you get the signal through that one. That means depending on how fast you are rotating this, with that frequency you can modulate that optical signal. Then there are other ways to do that. In optics, we have something called the photoelastic modulators. So that's made some straining. So there are so many different ways of modulating the signal. But when you modulate, you should know this frequency. At what frequency you are modulating it, right? This is a known frequency, modulation frequency. So this one also, if you have a chopper, you rotate it, let's say 10 Hertz frequency or 100 Hertz frequency. So we are rotating or modulating at known frequency. So yeah, direct only at. So then when you extract the signal from lock-in amplifier, you will see how we are going to demodulate it. Then we have to do some low-pass filtering. That's pretty neat technique. You will realize how that is done. So everybody remember this. If you have two signals, two sine waves, you can add or multiply, right? If you add, typically we get this kind of amplitude can go to zeros. So we call the beats, right? So if you multiply, they usually have some kind of this kind of features, right? Just take two sine waves and multiply and add and see how that goes. Very close frequencies. This is how the multiplied signal will look like. This is how the added signal, right? You know how beats work, right? If the frequencies are. So this is just to give. So, but in lock-in amplifier, what happens is, this is what I was talking about. So from the noise, how you take that real signal. So, I can go to next one, I think. Yeah. So the lock-in amplifier, what we have is, I said we have a signal, right? So now we are modulating with something called that frequency. In this case, we call it a reference frequency, right? So now we have this signal, we can write as the amplitude cosine omega t, that's a signal. Then we are referencing with some frequency that has additional phase here. So I will write, I think this is not exactly, this is what I hope I can write here. So suppose your signal is, say V signal sine omega signal, right? That has some phase, say signal phase, right? Now I am going to modulate with the reference. So that has reference voltage times sine, that has omega reference t, right? Plus, say, reference phase. So what we are going to do here, we are going to mix these two, right? That's like looking amplifier. What we have is signal. This is the signal. This is the reference. Then we have something called the mixer. Mixer means we multiply these two. So when you multiply, what do you get? We have Vs, Vr, then two sine terms, right? You know, two sine terms you can write as cosine A plus B, half of, yeah, half of cosine A minus B, right? This one minus this one, I write as omega whatever B plus phi minus phi S, then minus cosine, the sum, right? A plus B, so omega plus omega S T minus phi R minus phi S, whatever, you get the idea, right? So now when we do this one, so this has time dependence, right? Both of them. Now if I pass this one through some filter, what will happen? So if I take some low pass filter, so anything that has this T dependence will average out and cancel, right? Because any low pass filter means only the low pass thing, any frequency above that one, so that will, yeah, so that means anything that has time dependent part will be cancelled. So that means in this case everything will be cancelled except if omega r is equals to omega s, what happens? Then this is 0, that means that term doesn't have T dependence. Yeah. So only thing left is then is half Vs Vr cosine or sine, whatever. So that's cosine, yeah, cosine. This is 0. Omega r minus omega s is 0. Then you have just this phi r minus, we say it's phi. That is, phi means actually the phases between signal and this one. That's the whole idea. You can see when you pass through the low pass filter, only the component that has, like here, this is not very clear. So that omega r equals omega s, that means your reference frequency is exactly equal to the signal. That's the only part is going to be. So actually this is a DC signal eventually, right? This doesn't have any time dependence. This is really a DC. That's, you can easily take your signal, because this has that signal value, right, that you can take out from here. That's why we call it a phase locked, because phase is just the difference between the reference and signal phase. That's the way we use the locking amplifier. So you need to have your reference frequency. This slide is not good. I can give you a better one. So second term here. So this is not exactly what I want to say. You get the idea, right? So only the signal that has exactly the same frequency, that's the only signal you are going to be extracting. So this is typical what you are seeing, right? That's what I was telling you. This is your signal that has your DC component and noise. Then you put the reference, that frequency we know. Then we mix the two. So then you have to pass it through a low pass filter. Then output you get the real signal coming from here. So if you look at, so this is the mixed signal after this one. At the end, you are taking it as a DC signal. It doesn't vary, right? Because this doesn't have any. So this, if you look at this one, what you have here, it's all no time dependence, right? So it's only just DC signal. It's a very nice technique. So for example, if I want to use some impedance measurements, so what you do? So I basically, let me first finish this one. So if you talk about these low pass filters, ideally we like to have this kind of filter, right? So it's all the remember we talked about it passes only the low frequency part, right? So remember yesterday we talked about if you use one RC circuit, what do you get? 6 dB per octave, right? If you put 2 of them, you get 12. If you use 2 of them, then you can see it become much closer to this one, right? If you put 3, usually you get this one. If you look at any lock-in amplifier, you will see only these 3 options. You can pick whether you have 6, 12 or 18. This means having 1, 2 or 3 LC. These are basically RC circuits, right? That's nothing more than that. Yeah, so this is what I was talking about, right? Input mixer. Then this phase shifting means how you adjust this. This is your. This pi means pi r minus pi s. But what I want is this. This is what I need, right? That's the thing I don't know. VR I know because that's I give that modulation frequency. So I want, this is what I am going to measure in your, as a DC signal. Then it has, this is what I want to find. Since we know this one, we don't know this one. So that, but we know that since we are measuring at that particular frequency, then you can tune your frequency to get the signal to maximize your phase. That's because depending on pi r minus pi s, you can get that signal, right? Then you can adjust your phase to maximize that value.
And you're adjusting it so that way omega r and omega s are equal?
Equal, exactly, yeah. So because that's the only time you get DC signal, right? Yeah. Otherwise you have that T dependence. So there are so many. This is most of the lock-in amplifiers actually they have built-in synthesizer. So that way you can take internally that reference signal. So that all lock-in amplifiers you had to use some signal generator from outside to provide that reference. But nowadays everything they come with the built-in reference signal. But if you do some other experiment like chopper or something, then you had to use that chopper the oscillator to use the reference. So in that case you have outside reference. This is the lock-in amplifier. You have already built in one, or if it is not built in, you have to use from outside one. nowadays it's so easy since you have this built-in. So for very quick example, I can do. So if I want to measure impedance of some material, how do you do that? So this, everybody remember the impedance, right? That's basically di over dV, right? So one more. B over Y is here. So what we do is we just use some AC signal that I can get from the lock-in amplifier has its own synthesizer. So suppose this is grounded. So then we pass it through this sample. So before we do this one, I am going to modulate this signal with a DC signal. So that means I have this one, I put some DC, then I have some AC that can be say V0 sine omega t or something, right? So then what is your output is going to be VDC plus V0 sine omega t, right? This is summing amplifier that we talked about yesterday. Now I am going to input this one to my sample. This one, rather than doing this way, I am going to put this sum one. So then you take the output to your lock-in amplifier. I will draw a lock-in amplifier like this. So lock-in amplifier, you can either measure voltage or you can measure current. It has, if you look at lock-in amplifier, it has 3 inputs. One input for current, other input is for, we call the single-ended voltages. Other one we call double-ended, so this V and V. What does that mean? If you have some circuit, if you have something coming out with respect to, if you have 2 different, something like this, you have these 2 different voltages, right? In that case, you have to use this double-ended one. So sometimes you have your signal is with respect to some ground here. In that case, this is basically single-ended. You don't, because this is already grounded, right? So that's what this is. Whether you can have just single-ended one or if we have 2 different things like this. So if you have this one, that's pretty straightforward. Then I can write my total signal. So if I measure current, actually current is a function of both VDC and this one, right? V0 sine omega t. If you write this one, you can expand this one in a Taylor series, right? I have I, this DC value, then we have di over dV times sine omega t. Then I have plus half d squared I over dV squared times sine squared, right? Taylor series, then 1 over square, 3 times 2 d squared, 3, so on, right? But we don't consider anything. Actually, this is also very small. So now, if you measure this current, what is actually my value? That is 106 directly. If you connect it to lock-in amplifier, my output is directly, because this I am measuring at this omega t, I get directly my impedance. If somebody wants to measure the second derivative of this one, what you have to do is lock-in amplifiers have this something called harmonics. So this is omega t, right? That's we call the first harmonic. Sine squared omega t, you can write as sine cosine 2 omega t, right? Cosine 2 theta means 1 minus 2 sine square. So that means you can get 2 omega t. So that one is second harmonic. You can pick in the log-in amplifier with the first harmonic, second harmonic, third harmonic. If you pick the second harmonic, you directly measure what? D squared I over dV. It's very important. Sometimes you may have seen some signals. So they might look, if I have IV, if this is IV, so you can numerically you can differentiate this, right? Then you get constant, right? Di over dV is constant value. But you can directly, but if this has some features, Di over dV, this by numerically integrating you cannot get these features, but I can directly measure Di over dV from my log-in amplifier, right? Or I can measure second derivative like that. There are a lot of applications. Everything, if you want to measure photoconductivity or something, you just modulate your light source with a chopper, apply that chopper as a reference signal, you just measure it. So please read some about these things. This is really important. Important thing is what? You have to have a reference signal. So when the reference frequency and the signal frequency, when they are equal, that's the only signal survive when it passes through the low pass filter, right? Everything else cancels out. That's the neat part of that. Okay, so I'll stop here. Today we'll talk about this vacuum basics. So this also I already uploaded in the. Okay, so before we start the vacuum, so everybody should know the units, right? Typically, the CI unit, SI unit of pressure is Pascal, right? Pascal is a very small unit, that's basically Newton per meter squared. If you take 1 atmosphere, or 1 atmosphere is about 1 bar. 1 bar is about 10 to the power 5 Pascal. That's why Pascal is such a small number. So also, you know, in torr, right? Mercury high. So typically we have 1 atmosphere is about 760 torr. That means 760 millimeter of mercury, right? So that is 1 atmosphere is about 1 bar. So 1.0. So we can consider atmosphere as 1 bar. So 760 torr. So typically 1 atmosphere is, you can take as 1 bar or 760 torr. So here I didn't mention, but if somebody is working on gas pressure, so we see the pressure as maybe same PSI, right? That is pounds per square inch. That's how all the gas regulators are, I think, calibrated. So the unit is typically PSI. Typically about 52 or something, yeah. About 52 PSI, 1 PSI, we can say. So 1 atmosphere is about 14 to 15 PSI actually. About say 15, it's a good number to remember. About 15 PSI. That's why when we pressurize, remember we go to like 20 PSI or something, right? It's not too high. So about 15 PSI is about 1 atmosphere. That means I think 1 PSI is about maybe 50 torr, 52 torr or something. And that's reasonable, right? 15, this one is about 760, right? 1 PSI is about 50, say 50 torr. So that means 15 is about 750, that's close, right? Remember, this one also very important. So if you are working in the lab, so PSI is the unit for gas cylinders. So you don't want to go to like 100 PSI, right? As we are typically keeping around 50, 20, yes, that's very close, little above atmosphere. That's an important unit to remember. So then when you talk about the vacuum, what are we talking about? So typically we are reducing the pressure, right? Reducing the pressure means if you have a container, we are removing the gas molecules from the system, right? So that's what basically we are going to talk about. So that means if you have a really good vacuum, so what we are doing is we are reducing, increasing the mean free path for gas molecules, right? So if you have too many molecules, your mean they are colliding each other, right? So that means your mean free path is very small. But if you have a higher vacuum, they can travel farther distance, right, before they collide. So by making a good vacuum, we are reducing the number of particles. That means you are increasing your mean free path. That's the whole idea, right? So then the collision is typically the mean free path is given by this equation. So N is the number density, that means the number of molecules per unit volume. So D is the diameter of that gas molecule or atom. So you can get this one. Then everything depends on the kinetic theory of gases, right? I think everybody has statistical mechanics. So in thermodynamics class we learned about this Maxwell-Boltzmann distribution function, right? So everybody should know about how that if you look at any gas, there are three velocities we are talking about, right? So we are talking about average velocity. So these are typically average is given by this 8 kBt or pi m. Then there's something called the most probable velocity, that is given by 2 kBt over m. Then there's something called the root mean square velocity, right? RMS. This is given by 3 kBt over m. So if you look at the distribution, usually it has, this one has this Maxwell-Boltzmann distribution, right? This is a probability, how many particles for that velocity range. That's what this function is. This is the velocity. If you look at this one, typically this is the most probable one. So that is, or 2 times this one. Then the your so your root mean square value is here. Then the average value is somewhere here. So that is little less, right? This is the average value. So this is the most probable value. That's the maximum. Then we have the RMS value. So this, everybody should have some idea about these 3 values. So then when you talk about, then also we know how the distribution changes with temperature, right? When you go to lower temperature, they are very narrow distribution, right? So also the velocity values are going to be much smaller, right? If you go to high temperature, your average value increases, but it's a very broad distribution. This is like 1000 C, this is like minus 96. I think everybody's familiar with this one. But if you have a gas flow, you need to know this at least 3 different regions. One we call the viscous flow. Your gas is like if you are pumping gas or air from a system, right? So they go through different, we call the flow regimes. So one is when you have a lot of particles, or it's under high vacuum, right? High vacuum, no, it's a high pressure, low. That we have to be careful. If I say high vacuum means very low pressure, right? So high pressure means actually low vacuum, right? Yeah, be careful with that one. So if I have a container, so if you have a lot of particles, so that means your lambda is very small, right? Compared to this, this has some dimension, say some d. It's a 1/3 power of your volume, right? So typically, if this lambda is very small compared to d, so we call that a viscous flow. That means they don't flow very smoothly, right? They are colliding with each other. That's a viscous flow regime. So we call, when the lambda is very small compared to that dimension, viscous flow. But if you can pump enough material thing, then you have very few of these, right? So now I have only few particles like that. So now lambda is very large, right? So compared to d, so in that case we call this becomes molecular flow regime. So that's the regime we like to be, right? So
Yeah.
so reducing P will make it molecular, from viscous to molecular flow. So that means you have less contamination, right, in the system. So if you look at, this is where something called the Knudsen number comes into play. That's a very important number. This Kn is called the Knudsen number. That tells you the mean free path to that, the dimension ratio. If the typically this D is the container average collision mean free path. So typically mean free path you can write even in this. I will show you how to do that one. So viscous state, lambda is much smaller, right? Compared typically so in this case lambda over D is less than 100. That means your Knudsen number is less than 1 or 100. Right? So Knudsen number is lambda over D. In this case, lambda over D is less than 100. So if you take some intermediate state T's, so this is lambda is getting a little larger, but still much comparatively smaller than that dimension. But if you get lambda much larger than D, you get to this molecular regime. So you can see in this case your Knudsen number is greater than 1, right? Lambda over D is greater than 1. So that Knudsen number tells you your flow regime, whether it's a viscous or intermediate or molecular. So mean free path is the equation. I think we can easily derive this one. So how do you? It's very easy to make a. If you have some molecule or atom, so if it collides, if you have something, another one like this, if I draw the container like this, so this is more like, this is D, right? Like 2D. If anything going in this region, if they are colliding, if they are going above that one, they are not colliding. Then you can calculate the cross-sectional area divided by that. It's a very simple way to do that one. You can easily get this equation here. So this square root of 2 comes from that average velocity and things like that. So anyway, so you can see if you have, this is the equation. So lambda, it depends on T, right? If T is large, your lambda becomes large. So then also when P has to become low in order to have the lambda large, right? So if you put all this down, we know the Boltzmann constant. If I do at room temperature, we know T. Then if you assume some standard diameter for the molecule, so you can get this value something like this, pi over pressure in millitorr. So then your lambda is, so this is a very important equation to remember for anybody. So that way we know what the with the frequency how your lambda. We can see according to this one, if this is like, this is called a millitorr, right? At millitorr your lambda is about already 5 centimeters, that's pretty good, right? But if you can get to 10 to the power minus 10 torr, it can be kilometers, right? So that means you have very few molecules. Yeah. You can see what the viscous flow versus. So sometimes they call this intermediate, we call the intermediate flow. So that's what they call the Knudsen flow, when lambda is at the same size as the container size. So here is when you talk about vacuum, typically people talk about rough vacuum. So this means something. So Pascal, this is atmosphere, right? 10 to the power 5. If you get to like 100, so still it's a highly viscous flow, right? So they call it rough vacuum. So if you get intermediate, it can go down here. But if you want to get to really then high vacuum, good vacuum, ultra vacuum, and good ultra vacuum. So that means you need to have Pascal 10 to the power minus 10. So that's really, this is not torr, we are talking about in Pascal. So that, when talk about there are different vacuum regions people talk about. Typically in a lab, if you don't need very specific applications, we are talking about millitorr kind of pressure. But if you want to have some special situations, we can make like 10 to the power minus 6 torr. That's very easy to get. Like in our lab, we routinely work in like 10 to the power minus 6 torr regions. So then residual gases. So typically you start with air. So then when you keep pumping the system, so you don't remove everything, right? So first, when you do that one, what do you pump? Whatever outside air, right? So then, rough vacuum can only pump out those air particles. But if you go to kind of high vacuum, so you can even remove some of the moisture, water molecules attached to the surface of the container. They are very difficult to remove. So that's why sometimes when we do that one, we heat your chamber. So then you vaporize that. So then it's easy to pump, right? So you have seen like we call the baking system. So that's typically. So then if you go to a little higher vacuum, even hydrogen very small molecule, right? So they can be really attached to your surface. It's hard to remove with this kind of vacuum, but if you go to ultra vacuum, you can remove this hydrogen. So then noble gases like helium, argon, these things are extremely difficult to pump out. Because they can get into the surface and because they don't react with anything, right? So they can just breathe through. So then so also these residual gases, that depends on if you have some, say, chamber, so that has been open for some long time. So then that's going to be difficult to pump out. So that's why if you use the system when you, we call vent the system, so then immediately you have to pump back. If you leave it open for a long time, then it will be hard to pump back, right? So that's why it's important. If you have the residual gases, it depends on how long the vessel has been open and how it was vented. So suppose your system is, we are pumping, so at the end, I need to take thing out, right? Then I cannot open it under vacuum, right? I have to fill it with high pressure, right? So you don't fill it with air, right? You fill it with maybe inert gas, nitrogen or argon or something like that. So then you just remove it. So it depends on what, how it was vented, whether it was vented with nitrogen or argon, or maybe sometimes people in a hurry they expose to air. Right? So then next time it will be very difficult to pump. So yeah, so then whatever attached to the surfaces, they are very difficult to say. We have to have some degassing, so bake it or something like that. So vacuum systems are pretty tricky. So then also there might be some leaks, right? That's another thing to worry about. So then everybody familiar with vacuum force, right? If something, this is very important, like if I have some container, if I have very thin wall container, if I pump this one, what will happen? Inside pressure is very small, right? Outside is almost 1 atmosphere.
Yeah.
So then what? Look at the pressure. So you have huge force, right? So depending on that, this can be 1000 Newton. So if your material is not strong, what will happen? It just collapses. Yeah, that I have seen that's happening in aluminum containers. So you have to have enough strength to have. These are very important when you do these kind of things. So there are some constants everybody should be aware of. Avogadro number, universal gas constant, Boltzmann constant, and things like that. So you know how to calculate if I give you pressure and volume and how many particles there, right? So you know how to calculate all this. There's a very important another aspect, something called the impingement rate. This means if you have some surface, suppose I use a very high vacuum system, it has some sample there. So the moment when I expose it to some pressure, immediately these molecules will stick onto the surface. That's depending on the impingement, right? It comes, sometimes it can get reflected, most of the time they just stick into this one. Right? So that's the impingement. So you will see it takes less than second to make a monolayer even at that high vacuum. So that impingement rate is given by this equation. Again, very easy to prove this one using the molecular gas theory. So this is called the number of molecules striking a unit area of that surface. So then most of the time when it sticks to the surface. So that's given by this N is the number, the density. That's N over V. So typically, yeah. So this impingement rate is given by this the number of molecules per unit time. That's what this one. So this is N, the average velocity. Remember, average velocity is given by this 8 kBt over pi times m, right? So this is 1/4 of this one. So N means number of molecules per unit volume. So then we know V is given by NKT, right? So then if you substitute these ones, you can get this equation easily. It's very easy, right? So this is 1/4, N is N over V, V bar is this one, V over pi m. Then if I take this N inside, this becomes N squared, right? So substitute N squared here, then you get P squared V squared over KT. That's how this KT comes out. P squared square root, that becomes P. You can easily get this equation, right? So you can see now impingement rate that increases with P, right? If the P is higher, definitely you get more and more molecules in. So at high temperature you have less, right? Because they can even get reflected, and so the rate, the velocity is getting higher. So, yeah, this is important thing. See, for a residual vacuum of 10 to the power minus 6 torr, that's not a bad vacuum. If at this, because for that pressure, if you calculate, your pi becomes this number. This means deposition rate of the residual gas 1/3 of a monolayer of solid per second. For 1 second, even at this pressure, it can make a monolayer in per second, 1/3 of a monolayer. Monolayer means one complete molecular layer is deposited on the substrate. 1/3 of that can happen in 1 second, even at this pressure. That's pretty, so you can see, right? So if you want to have a clean surface, you need to get to at least 10 to the power minus 10. Then you will see this number become much smaller, right? That's why it's very hard to make a perfectly clean surface, because it always has the atoms impinged onto that one. And you can calculate that one from this one. Collision distance. Here I have the collision distance for different pressures. Okay, yeah, let's stop there. So now let's talk about vacuum pumps. So to get to this pressures, we have to use the pumps, right? So pump, if you have a pump, suppose this is my pump. So pump is weighted as is pump speed. What's the pump speed? Pump speed means how much volume you can reduce for a given time, right? That's why we call the pumping speed. S is given as dV by dt. That's the volume of how much volume you can remove for a given time, right? That's what pumping speed means. Then we call something called the transmission. That's the important name. Transmission of the pump is given as, we have certain pressure here, right? That pressure times this S is called the Q. Q is called the transmission of the pump. So this is just for the pump. So that's why if you pick a pump, first we need to know what's the speed of that pump, right? So this is about the pump side. Now when you use pump, you need to connect the pump to your, this is my pump. You have to connect your chamber, and this is the chamber. You have to connect with pump, some pipes, right? So these are the pipes. It can be tubes, or it can be rods like copper tubes, or it can be, we use some Teflon tubes, anything, right? So when you have that one, we have to define this kind of transmission for the flow of those molecules through that pipe. So there are two things you have to be separate. One is this pump as this transmission. Next one is we call this transmission, but for the pipes. So, or we call the conductors. So if we have this pipe, then pipe should have two different pressure at the two ends, right? So then this transmission is, we call that Q. Here we transmission of the channel now. Previously transmission of the pump side, right? So that we define as, so this is for the pump side. This whole thing is about the pump side. So now the channel side. Channel is that whatever you connect here. So that we define this Q, just like this one, you have this pressure. Actually in this case you have the pressure difference, P1 minus P2, right? So then S is in this case the pumping speed. Now in this case more like we call the conductance. Conductance of it, just like electrical conductor, right? The electron flow. Now here you have molecular flow, right? So that we call this times your Q, the C called C. C is called the conductance. So O1 over C is more like a resistance. resistance for the flow. So that means it's harder to pump, right?
Mm.
So if you take a really narrow tube, then your conductance is smaller, right? Because it's a much higher resistance. If you have a larger tube, then your conductance is higher, right? Because it's easy to flow. These two equations are very important. But please remember, this is for the pump, this is for the channel. So channel has two different pressures, right? So pressure inlet and pressure outlet. So C is called the this conductance, but it is pretty similar to this one. So in this case, we have the pump speed, that is also meter squared per second. This C also has pretty much same thing, meter squared per second, but that is mostly flowing speed. So with this one, everything is now like making electrical circuit. So basically you can put parallel lines or series lines and things like that. That's how you design pump system. So typically if you have these conductors for a channel, right? If you have a very long round tube, you typically that conductance is given by this equation. If we have a long round tube because it's more like there's viscous flow and laminar flow and things like that, so we have this equation. But if you are in a molecular flow, that's what we are interested, right? At very low, very high vacuum or long mean free path. So actually that number doesn't depend on the pressure. So that's a good thing, right? So this is independent of pressure. It only depends on the dimensions of that tube length and the diameter. Everything depends on the length and diameter, definitely, right? All three. So yeah, this is what we are talking about. Remember when you talk about S is the pumping speed, right? So Q equals PS. So then, yeah, so that is then for the channel. So when you make the systems, so please read all these things. This is the equation for the, we call the throughput of the pump. So QESP, this is the, for the channel equation. Now if you want to make like several tubing in parallel, suppose if I have a system, so I may have to have 1, 2, 3 like channels connecting to something. So they are parallel, right? So then you have to add as the, like just like your parallel resistors. This is your total your conductance, right? So then if you want to have the total effective conductance, remember S is more like this Q is S times your P, right? So this S also dV by dt. So then for the channel it is Q is more like P1 minus P2 times C. This is also dV by dt. So they both are having similar function, right? So that's why you can take S and C effectively. So that is, so you can write as effective S is this effective C. This can be 1 over C, all the composite one, plus 1 over that S. So that's what this is about. So this way you can get all the information how everything is done. So you can write the equation for this one easily, right? So here you can say Q in. So in this case you can say this pressure minus this pressure is what your this equation, right? So then from here to here again, this you can easily write this equation. So ideally, when you design some system, we have to be very careful with these things. How large tubing you have to use. I have seen people like they have this big chamber. They use this small tube. you can see then the conductance is very small, right? That's not the right thing to do. So compared to the chamber, you need to have right tubing. Yeah, on these things. Yeah, then you can look at how the pressure changes with time when you start pumping. That you can easily do by this equation here. So we talk about this one, right? So now if you start the pumping system, your equation, dynamic equation, you can write as, remember this S times P means this Q, right? The pumping side, so then this is the channel side. So that will be again, like I said, they both are more like dV over dt, right? So that I can write as, since it is SP, so this is more like dq over dt. So that means, but volume is, so if I write this one as dV by dt, so since I have to have Q, this is dV by dt, right? So this is more like P times dV by dt. So, or if I write this one like d over dt dV, right? P is a constant in that case. But if you have a chamber, in the chamber, volume is constant, right? Then I can take V out. So then it becomes dP over dt. So, but we know when you pump, your P is decreasing with T, right? So that's why you have a negative sign here. Now you have a differential equation, dP over, you can take this P down, so then you differentiate, you get logarithmic P. So then when you do that one, you get exponential. From here you can get the equation like this one. So this is the equation. You can easily solve this one, right? First order differential equation, dP over P. So this is the equation. You can see early stage pressure changes like this, and then it reaches this constant value. So you can estimate how your system is going to be pumped down over time. So, okay, so outgassing, that's another thing. If you are using some good vacuum system, these are the elements you should avoid. It's called the blacklisted element that has very high vapor pressure, like magnesium, lithium. These things are very bad thing to use in a vacuum system.
What is the reason that they're bad for the vacuum?
So they have very high vapor pressure. So that means even at room temperature, a lot of vapor is there, so they can get attached to the
surface,
the chamber walls, and it's very hard to degas. So you can see most of these things are not common things, right? Bromine. Bromine is actually, everybody know bromine, one of the elements that's already liquid at room temperature, right? Gallium and mercury and bromine. Actually bromine, even at room temperature, it vaporizes. Very nasty gas. Iodine, mercury, all these are all alkali metals, right? Lithium, cesium.
The zinc?
Zinc is not there. Zinc also, that's not alkali metal, right? So you can see these are not very common materials you use in a chamber.
Mm-hmm.
Yeah. Outgassing, so if you want to outgas, you have to first make sure you don't use these blacklisted metals, first thing. Then, if you have to get a good vacuum, you have to bake out. So how do you bake out? Usually we put these electrical tapes around that and apply large voltage to heat them, right? So heat it. So you can see sometimes these big vacuum systems, they do the experiment for certain times, then they take time off and do the baking. They have to cover everything with aluminum foil and put tapes all around and bake it for maybe several days. So then only they can get to the low enough pressure. then whenever you are venting, use some inert gas like nitrogen or argon. So we'll talk about skater materials later. So sometimes we can use plasma to clean. Okay, so typical vacuum system. So how do we make some typical vacuum system? So I think next time I will talk about all the different pump system. But if you want some simple high vacuum system, so this is the chamber I want to pump. So if I connect it to a simple mechanical pump, so it's not, this is a mechanical pump here. So I can get to maybe millitorr, so but that's not good enough, right? So what we do is typically, this is my chamber. So typically this has something called gate valve. So then later I'm going to talk about this simple mechanical pump that is good. Also they are the roughing pump. That's good for rough vacuum. Then there are pumps, they are good for very high vacuum. They are called, there are several things. We have the diffusion pump. I'm going to talk about all of them separately. Diffusion pump, then we have turbomolecular pump, turbomolecular pumps, then we have ion pumps, then we have cryo pumps. These are for very high vacuum. But you cannot get to high vacuum unless you first rough the system. You need to first get to at least not to the molecular regime, at least that intermediate, not from the viscous, from viscous to intermediate. Then you use these pumps to get to the lowest vacuum. So this is how it's working. So this is the chamber, right? So I have something, say some special gate valve. So then I have to, yeah, so before that, just put the gate valve toward it. Let me explain from here, that's easier. Yeah, so this is the chamber I want to pump out, right? I need to get that to 10 to the power minus 6 or 7. So this is some special gate. So then this is the pump. It can be one of those pumps I was talking about here. So they can be, this is actually the diffusion pump that I have in one that downstairs here. So then this is connected to a simple roughing pump here. You can see here, right? This is the roughing pump. So what we do is, first, these are two valves. So everything is closed. First, I start the mechanical pump and open this valve. Then what happens? Pump on this system. But it cannot get to very low. It can get to maybe intermediate region. So then, it's already under some vacuum, right? It's not atmosphere now. Then this one. Then we open this one. So then, it's already under some rough vacuum. Then immediately this will take over. So then it will go to very high vacuum. But this is, I think, already doing too much work to do that. So then, since we isolated this one, we open this one and pump on this one. We call that a backing pump. So you back it, because this is doing too much work, right? So to back that one, we just open this one. This is closed. So then this is working on this chamber. So at the same time, you are helping with this one. At the beginning, this was a roughing valve. At the end, this is a backing valve. So that's basically how it works. So actually this one has, so this is the mechanical pump. This is the, yeah. So basically, how does it work? Yeah. So when you do the experiment, first you come here. First thing is to do is actually, that we don't know, right, how this one works. That I will explain later. First thing you do is, you have to make sure this is closed. And this is also closed. Otherwise, if you, sometimes actually you can clean everything by opening both of them so that it can pump like this and clean everything. But when you do the real experiment, this is completely closed. Open this, rough it, then close it, make sure you close it, then open the gate valve, then it's pumping. So then open this one. That's it. So when you do this one, you can get to clear it over. This can be, actually, there are systems they use diffusion pumps, so there are systems with turbo pumps. I have a couple of turbo pump systems if you remember there. The diffusion pump system in this building. Then also we have some iron pump also. So that's basically how things work. So these are some of the pumps. Maybe I will do this one in the next class. This almost done. Yeah. So in next class I'll talk about all kind of pumps. So I think mechanical pumps everybody familiar, right? So what does it have? It has this kind of thing. So this is the system I want to pump, right?
Mm-hmm.
So what I have to do is first I just trap this air here. So then this is rotating. When it rotates, so you can see you just bring it to this region and just push out, right? That's the exhaust. So that means you remove some of this, and then it keeps doing that. But then it takes another volume of gas. So if we come here, then you can see now it is trapped here, right? So that will open this one and just go. So by doing this one, you can remove most of these gas molecules. That's what you want, right? You have to remove these air molecules from the system. Just basically, this is kind of this mechanical pumps you are going to see. But you have to make sure you have enough oil and things. So then this, there's called some rotary pumps, very similar to this one. So it's the same idea. So you can see they have this rotating drum. So again, same thing, you just take something from here, like this one, then rotate here, then you trap this one. So then the next round you are going to exhaust it, then come back and keep doing this one. So then there's a very special one called some gas ballast, these mechanical pumps. This one is important because sometimes if you have some say some this residual gases or maybe some unwanted vapor in the system. So then it's very hard to pump that one, right? In that case, we provide little bit air from here, so that will help to clean up that oil, what you are coming from here. So this is little bit more contaminated with some, say, oil vapor or something. So that one, the same rotary pump, but we have this gas ballast, so that will introduce some air. That air will clean up that thing, so that will help it to. Yes, actually that works really good. So this one will the ballast. Yeah, so we'll talk about these things next. The diffusion pumps. So I think I need about maybe 10 more minutes next class. Okay, so please read these things. So then we talk a little bit about leak checking. How to check whether your system is leaking. How do you expect if you have any leak in your system? That's the most difficult thing, right? So one way to do is just pressurize it and use some soap. If there's any leak, you will see some bubble, right? So, but that only you can do if it is a big leak. But if you have tiny leaks, it's very difficult. Yeah. That's where we use something called the helium leak detectors. You pump the system and introduce little bit helium, Then if there's a leak, helium will creep through, so that will be detected by some mass spectrometer. Okay. These are my comments. So we will meet again next Tuesday, right?
Yep.
Has there classes shown up on Whiteboard for you? What's the 2-3 class?
No.
No.
I'm doing,
Huh?
I'm doing that.
Oh, sure.
2 to 3 hours.
Yeah. Yeah, the classes haven't shown up yet.
We have to, to observe, we didn't detail material, right?
Yeah, I haven't seen it on the platform.
No, the class is there on the blackboard.
Oh, really?
Next
Yeah,
Thursday.
Since yesterday.
We need to discuss,
Oh, it's most likely your qualifying exam is going to be next and the following weekend. So I,
Next week.
no, next week means I think 21st and 28th something. Yeah, so I will send the email. So Jane told me like unofficially. So she was asking me, I think it should be okay, right?
21?
Yeah, Saturday and 28th other Saturday.
21 is too
Huh? It's too fast.
fast. Too fast,
You think so?
And one,
they want more time to study.
yeah, so we have two subjects that will be held, I think, the first day.
Oh, they both are on the first
Yeah,
day?
yeah. In the fall, the first day, 2 exams, there was.
So then how about like 28th and the following week?
Yeah.
That's
Yeah.
28th.
Yeah.
I'm excited. I'm gonna be learning.
I will tell them.
Okay, so the 28th and like, you know, like.
But in February, right?
We are also expecting that.
What's that?
We are also expecting our qualified will be 20th
Yeah.
and following.
Yeah, she told me this, yeah.
January is.
Yeah, I
I thought January is.
Yeah, because most of the people are here, right? Except Kai.
So
Yeah,
Kai is
yeah.
21.
next
Yeah.
week,
Yeah,
I
okay.
want to read the.
Okay, then I will.
So that way you can ask
Yeah.
questions.
Please turn off the light before you.
Okay.
And then Friday, then you can do the last But you can read through the lab manual.
We were gonna fight for that. Yeah. I was like, 21st?
21st is
Holy
too
shit.
It's only one week.
You wanna get together Sunday and Monday?
Okay.
Sunday and Monday?
Okay,
Okay, and probably every day next week.
okay, every day.
But like a Sunday and Monday for sure.
Yeah.
I'm gonna meet rain, snow, or no show.
21 is, I thought 21 is too fast. Since we have 2 subjects that will be in the 21. If 21.
Yeah.
Yeah.
Let's see. So that's classical and E&M.
Yeah.
So I think for the next week until the 28th, we should do nothing but classical and E&M. Just to
Yeah.
get those 2 out of the way, because they can only ask so many stuff on quantum.
Yeah.
Like free particle
Yeah.
in a box.
Yeah. Priority density function, normalize it.
Yeah. Orthogonal functions.
Yeah.